Looking at the hypothesis test, we've already seen what we can do when sigma is known, but many times sigma is unknown, as we've talked about before. So if a test needs to be conducted, but that population standard deviation is not known, our best guess for that population standard deviation is the sample standard deviation. Therefore, replacing the population standard deviation with the sample is an easy fix. Or is it? The above formula poses a problem that we've already seen when the confidence intervals were discussed. It has two parameters from the sample. This makes using the normal standard distribution or z-statistic a problem, and we need an alternative approach. The approach is that when sigma is unknown, we replace the population standard deviation with the sample standard deviation. With the two parameters from the sample, now the t-distribution is used. Easily enough, the formula is the same. Just replace the sigma with an s, and the calculation is now our t-statistic. But now again, we will need something else. Recall that when we use the t-statistic, we're going to also need the degrees of freedom. So consider the sample from the previous module where a sample of 100 observations are collected with a mean of 50. The population standard deviation is unknown, so we will use the sample standard deviation. From this point, the calculations are still fairly straightforward. We do everything the same way. Our x bar is 50, s is 4.5, n is 100, mu is 51. X bar is 51, x bar is not equal to 51 is our null and alternative hypothesis. We plug in all the numbers and we get a t-statistic of negative 2.22. Now the p-value of the t-statistic needs to be computed, but remember that we require the degrees of freedom, which is the number of observations minus 1. So in the example above, since the number of observations is 100, our degrees of freedom will be 99. Note that this is a two-tailed test, and so there are two formulas that we can use. We can either use the t.dist or t.dist.2t. The x will be the same and the degrees of freedom will be the same, and true is whether it's going to be a cumulative on the first one. There is none for the second one. The real difference comes in with this, is that if we're going to use the t.dist itself, we need to multiply this by 2 to get the areas of both tails. Remember, if we do the t.dist, it's only going to give us the left tail, so we need to multiply it by 2, and that'll give us a value of 0.0287. If we use the t.dist.2t function, again with the same number, this will give us the area in both tails, and it will give you 0.0287. So with the p-value obtained, our rejection region can now be determined. Assume that alpha is 0.05. Since the p-value is 0.0287, it is less than 0.05, we will reject H0. Thus, we have support that the sample mean is not equal to 51. In the one-tail test, again, we'll do the same general approach. Assume the marketing manager wishes to determine if revenue rose from a marketing campaign. The historical sales were 47.89. After taking a sample of 100 receipts, the sample average is 48.5, with a sample standard deviation of 1.22. Nothing has been said about the population standard deviation, so the sample standard deviation needs to be used. We set up our pieces again, and we set up our null and alternative hypothesis using the less than or equal to and a greater than sign for the alternative hypothesis. We compute everything pretty much the same way as before. In this case, we've set everything up and we've computed the t-statistic to be 5. Because 5 is positive, we're on the positive side, we're going to do 1 minus because it means we're on the right side of this distribution. 1 minus t.dist 599 true. Our result is going to be 0.000001. That gives us the area for the right tail. Since the null hypothesis is less than or equal to, this is a one-tail test, and the alpha value will be compared directly with the p-value. Since 0.00001 is less than 0.05, the null hypothesis is rejected, and therefore we have evidence that the sample mean is greater than the expected mean, and therefore the marketing campaign seems to have worked. We set up our summary again here, again with our hypothesis in the lower tail, and the hypothesis in the upper tail, and the hypothesis in the two-tail. Everything is pretty much the same. The t-statistic is computed and it's the same across all three as well. we can show again, doing the same thing, that we can use the t-statistic and compare it to a t-critical value, which usually is obtained from the book or is obtained from a set number. The z-critical and t-critical values are very close to each other. The more observations you have, the closer the t-value will get to the corresponding z-value. So if your alpha was 0.05, your z is going to be 1.645. If your alpha is 0.025, which is again that 95% confidence interval, splitting the 5% into two tails, your z is 1.96. And if your alpha is 0.01, your z is going to be 2.32. Well, look what happens to the t-critical value as you get a larger number of observations and corresponding degree of freedom. For the first row, it's 1.83, and then it goes to 1.67, and then it goes to 1.66, which is very, very close to that 1.645. With the 0.02 alpha value, t becomes 2.262, 2.010, 1.984. Again, it gets very close to z. So this table shows how close the values get as the number of observations increase.